Hi everyone, Miss Lorette here. In this video, I'm going to be walking you guys through section 7.4, which covers a couple of division properties of exponents. You'll want something to write with and something to write on, and possibly a calculator if you feel like you're going to need it. And the first property that we're going to talk about is when we're dividing powers with the same base. When we're dividing powers that have the same base, we're going to subtract the exponents. And there's a couple of different ways to figure out why we're subtracting the exponents here. When we learned about multiplying powers that have the same base, we learned that we could add their exponents. So you can almost think about this in terms of inverse operations, right? What's the inverse of multiplying powers that have the same base? Dividing. So then what's the inverse of adding their exponents? Subtracting. Another way that you can think about it is in terms of negative exponents. We learned that when you have a negative exponent, you take that power and you move it to its reciprocal location. Well, the reverse is true. If you take something that has a positive exponent and you move it to its reciprocal location, rather than making a negative exponent a positive, you're going to take that positive exponent and make it a negative. So I could take this power in my denominator, move it to its reciprocal location, and change the sign. So it's going to look like this. And then from there, I can actually just use my multiplication property that I learned in the past, where I take these two exponents and I add them. Well, m plus negative n, that's the same thing as subtracting. So a couple different ways that you can figure out why we're subtracting the exponents here. And again, we're assuming that our bases are not 0 to avoid any undefined cases, and that m and n are rational numbers. Let's take a look at some very basic examples, and then we'll increase the difficulty as we go along here. I have 2 to the power of 6 divided by 2 to the power of 2. My bases are the same, so I can subtract their exponents. And whenever you're doing this, you're leaving the base of 2 the same and subtracting the top exponent and the bottom. You're always doing the top exponent first and then subtracting the bottom. Also, whenever you're using this property, you're then looking at that base as if it's in a numerator position. So notice we went from something that had a fraction bar to just something that is understood to be a numerator value because there is no fraction bar. And then I can simplify. 6 minus 2 will give me an exponent of 4. And then since my base is a number here, I can go all the way and simplify this. And hopefully my mental math is correct. It's the end of the day here. And I've tried recording this video multiple times, so I'm hoping I can just kind of get through it at this point. Okay, let's take a look at number 2. I have x to the power 4 divided by x to the power 7. I can leave that base in x, treating it as if it's in a numerator position now, and take the top exponent of 4 and subtract the bottom. That's going to give me x to the negative 3. Now this is not fully simplified due to the negative exponent. I have to take that power and move it to its reciprocal location for my final answer. So for my final answer, I'm going to be left with 1 over x to the positive 3. For number 3, we've got fractions, but I still can use that same property, which tells me that if my bases, which are s, is the same, I can take that base and subtract the exponents. And in order to add or subtract exponents, in order to add or subtract fractions, their denominators have to be the same. Well, my least common denominator between 4 and 2 is 2. So I'm going to just multiply the second fraction by 2, so I get a denominator of 4, and now I can actually subtract the exponents. I'm going to get s to the 1/4, and I cannot simplify that any further because s is not a number. Or at least I don't know what number it is. Okay, let's take a look at some more examples. And of course, if I'm going through these slides too fast, always feel free to rewind, pause, do what you need to do to make sure that you're getting all of the examples and understanding. Now we've got multiple powers. Take it one power at a time. I'm going to look at the variable m's first. I'm going to treat it as if it's now sitting in a numerator position and do the top exponent minus the bottom. And I'm going to do the same thing with my variable n. I'm going to take the top exponent, subtract the bottom. For my exponent on the m, I'm going to get a -3. For n, I get a +1. I can take this power of m to the -3 and I have to move it to its reciprocal location. The n can stay on top, and I don't have to write the exponent of 1. That's understood to be there. So this is what I get as my final answer. For number 5, we have a base of 3 to the power 5, and then 3 to the power 3. Same thing, I'm taking that 3. You're not dividing the 3's and getting a 1. Remember, you leave the base the same, and you're subtracting those exponents. And then I'm taking that power of k and subtracting the exponents here. So I'm doing the top exponent of 2 and subtracting a -4. These double negatives turn into a positive, okay? So the reason why I got double negatives here is the first subtraction is because my property tells me I need to subtract, and the second subtraction comes from the fact that this exponent was a negative. So you do need 2 negatives here, and they're actually going to turn into a plus. So rather than subtracting here, I'm going to actually add. And then for my power of j, let me move this down here so it got a little more space. Remember, you're not just doing to the power of 4. You're subtracting that invisible exponent of 1 on that bottom j. So we end up getting 3 to the +2, k to the +6, and j to the +3. I can then further simplify that 3 squared to get a 9. Here's my final answer. For number 6, I'm going to leave my base x the same, subtract the top exponent and the bottom. Leave my base y the same, subtract my bottom exponent or subtract my top exponent and my bottom. Again, we're doing a negative minus another negative, so 2 negatives will make this a plus. We're still going to end up subtracting here though because their signs are different. I've got a negative and now a positive. And then z to the power 8 minus that invisible 1 that's understood to be there. This is going to give me x to the power 0 times y to the +4 times z to the +7. And anything to the power of 0 is understood to be a coefficient of 1. And I don't need to write that in, so I can just write my answer like this. So here are a few problems for you to try. I encourage you to pause the video and give them a go here, and then I'm going to scroll to the next slide, which has the solutions. Okay, so hopefully you have given those a go. Number 7 in particular, I'll kind of zoom into these one at a time so we can really go over them. Number 7's a little tricky. You're not just writing -3 to the power 2 minus 5. Okay, this negative is actually not a part of either of these bases. It's not in parentheses, so you have to treat them as if they're coefficients of -1s. We multiply and divide coefficients just the same as we always have. So -1 over -1, they're going to cancel out. When I divide it, I get a positive, and I don't have to write a +1 in front of my power. A +1 coefficient's always understood to be there. So really what you're doing here is a +3. That's really your base here to the power 2 minus 5, which gives me -3. I can then move that to its reciprocal location and simplify. So be really careful when you see negatives in front of your powers. If you don't see it in parentheses, then it's not being affected by those exponents. It's actually a coefficient of -1. For number 8, you're going to end up getting double negatives when you go to subtract. giving you a plus sign, but you end up subtracting the values anyways because their signs are different. The first exponent was negative, and then you end up getting a plus. For number 9, my work starts up here. I'm subtracting 1/4 and 3/2. I need to find their common denominator of 4, so multiply that second fraction by 2. That's going to give you 6/4. When I initially subtracted, let's see. Oh, you know what? I actually made a mistake on this one back when I did it. So I'm going to go ahead and fix that here. Let me just erase all this. It's a good thing I'm going over this in detail. 1 minus 6 is going to give me a negative 5/4. And then that negative exponent tells me I still need to move this power down to the bottom. So here's what we should get as our final answer. Just made a little, oops, not a negative, it turns positive. I just made a little error here. Okay, hopefully that's correct now. All right, zooming into number 10 so I can kind of show you where the work starts. Here's my first step right here. I took my power of j, subtracted the exponents, k, subtracted the exponents, and then this is what I got as my final answer. Remember, you've got that invisible 1 that's on that k. It's not 6 minus 0, it's 6 minus 1. Number 11, I think, was also another tricky one. Okay, the negative 2 and this 4, the first numbers that I see, they don't have any exponents other than a 1. So they're actually not truly part of a power. Okay, so you treat them as coefficients here. These other exponents, they're not going to impact this negative 2 and this 4 because they're not sitting inside of a set of parentheses where the exponent's directly outside. When that's the case, the only thing that's affected by the exponent is the thing that it's directly touching. So I treat them as coefficients. So I can multiply and divide coefficients the same way as I always have been able to. But because I don't get a nice integer, I reduced it to a negative 1/2. And then remember, when you subtract for these powers, these exponents here, when you have matching powers, subtract the exponents, but you treat that power as if it's then sitting in a numerator value. So I wrote my power s in the numerator, subtracted my exponents, and I did the same thing with my power with base r. I ended up getting a negative 9 as my exponent on the s and a negative 1. So both of these end up moving down to the denominator where my 2 is. So this looks like a 5, but it's not. This is a 2s. Let me try writing that a little clearer. This is an s. 2s to the power 9 times r to the power 1. And notice I don't have to write that exponent of 1 on the r. It's understood to be there. And then number 12, careful with this one. We've got a, b, c up top, but then a, b, z on the bottom. So for that last variable, you're actually not going to subtract here, so be really, really careful. The only ones that you're subtracting, and again, I'm putting them in as if they're in a numerator position, is for the variable a. You're going to get double negatives, which change to plus, and then for b. The c just stays up top, and for now I put the z where it was. I simplified for my exponents and got positive 5 and negative 8. The negative exponent on this b tells me to move that power to the bottom. The z has to move to the top. So this ends up being my final answer. The next property that we're going to cover is when you have a quotient that you're raising to a power. So this is very similar to a power or even a product to a power. You're going to do the same thing. Whatever exponents are on these powers, you're just going to take the outermost exponent and multiply. Okay, and the reason why we're not subtracting exponents here is because these bases are not the same. We have a base A over a base B, so I cannot subtract their exponents here. Again, any base we're assuming is not 0, and our exponents we're assuming are rational. So let's take a look at a few examples here. Some basic ones to start off. Okay, so we've got a quotient where my bases are different being raised to an exponent. They have their understood exponents of ones. I can't subtract them because the bases are different. What I can do is take that outermost exponent on the outside of a parentheses and multiply. That's going to give me 3 cubed over 5 cubed. And I can further simplify these to give me 27 over, I think that's 125. Hopefully my mental math is correct there. Also, if you're wondering if this massive fraction reduces, a quick way to see if it reduces is to check if your first fraction reduces. Always reduce first before using this property rather than after, okay? If the first fraction can reduce it first, then use your property for your exponents. If it doesn't reduce, that means your final answer is going to be fully simplified. You can't reduce this either. For 14, both of these bases have understood exponents of ones, and I cannot subtract them because the bases are different. I have a base x over a base y. All I can do is take this outermost exponent outside the parentheses and multiply, and that's simply going to give me x to the power 5 over w to the power 5. And again, this is fully simplified. I cannot subtract those exponents. The bases are not the same, so that's done. For 15, I've got understood exponents of ones here, and we've got a fraction as an exponent, which is okay. Fractions are still rational. 1/2 times 1 just makes this a 1/2 on both of my powers. And that's as fully simplified as I can get. I cannot subtract those exponents. Those bases are different. Let's do a few more complicated examples. For number 16, I'm going to take this exponent of 2/3 and multiply it with 3. That's going to give me a 3. You may want to do that work off to the side if you need to, but 2/3 times 3, oh, excuse me, not 3, that's the red. You could probably tell I'm a little tired while recording this video. It should give us a 2, okay? 2/3 times 3, those 3's are going to cancel, leaving us with a 2. And then 5 is being raised to the power of 1, so it's now going to be a 5 cubed, which I can then further simplify to give me 125. Here's my final answer. Number 17. If you notice on the inside, I've got some matching bases on the top and bottom. So here we're actually going to combine those two properties. I like to kind of simplify the stuff that's inside first before I distribute this 2 to every single thing, because then you're multiplying this 2 with fewer exponents, hopefully. So on the inside of my parentheses, again, I can treat the bases as if they're now in a numerator position when I use my property that says if your bases match, subtract the exponents. So I'm going to write base x as if it's a numerator position and subtract my exponents. And I'm doing 2 minus a -1. This turns to a plus. And this is also being multiplied with a base y. I can do the same thing here. I can write my base of y as if it's a numerator position and subtract the exponents. Now, as I'm doing all of this, this is all still sitting inside that parentheses with the exponent of 2 on the outside. I haven't done anything with that yet, so I need to be careful and actually bring down the parentheses in this step. I'm going to simplify here a little bit. Again, it's still in parentheses. X now has an exponent of 3. My y has an exponent of 1. And now I actually have, rather than a power of a quotient, I actually have a power of products. I still do the same thing though. I'm taking this outermost exponent and multiplying, and that's going to give me x to the positive 6 times y to the positive 2, and now I don't need the parentheses. And then for 18, same idea. I see some matching bases here, so I'm actually going to simplify the stuff that's in parentheses first. Base A, I write as if it's a numerator, and I subtract the exponents. Base B, I write it as if it's in the numerator. I subtract the exponents. Remember, there's an invisible 1 here. C to the power of 8 is already in the numerator, so I can just kind of bring that down in my work. And this is all still in parentheses, being raised to the power 1/2. I'm going to simplify my exponents a little bit. I'm going to get positive 2, negative 4, and then I just bring that c to the power 8 down for the ride. All being raised to the power 1/2. Last but not least, I can distribute or multiply that 1/2 to everything inside. That's going to give me positive 1, negative 2, and 4. And then this power with base B has to move to the denominator, which is going to give me, let me shrink all this just a little bit, make some more space. That's going to give me a to the power 1 times c to the power 4 all over b squared. So here are a few for you to try. Again, I encourage you to pause the video, give them a go. And then on this next page, I will show you most of the solutions. I had to put 24 on another page because I simply did not have the space to write it out on the slide. So let's take a look at each of these, also double checking my work, make sure there's no other errors here. For 19, you're going to multiply that exponent of 1/2 to these understood exponents of 1s. And remember, when you've got a fraction as an exponent and your base is a number, that denominator of that fraction exponent, of that rational exponent, it's actually asking you how many times, or what number are you going to square, what number are you going to raise to the power 2 to get this base of 4. In other words, you're taking the square root of 4. Okay, this is actually a radical with an index of 2. So the square root of 4 is 2, or in other words, I could square this 2 to get a 4. Notice that when you do this, again, this is a bit of review back when we covered these types of problems, that when you do this, your answer does not have an exponent on it. Same thing with 49 to the power 1/2. This denominator is asking you what number would you square, would you raise to the power 2 to get a 49? Or in other words, what's the square root of 49? That's going to give you 7. So you end up getting 2 over 7 as your final answer. 20 was pretty quick and easy. You should just get a to the 3rd over b to the 3rd. And then for 21, you've got a lot of different things going on here. So to make sure I can, write everything out, I wrote it above. You're just taking this 4. Every single value here has an understood exponent of 1. So you're multiplying that 4 to all of them. And then the bases here, I can further simplify them. 2 to the power 4 gives me 16. 3 to the power 4 gives me 81. And that's my final answer. For number 22, 4/5 times 10 gives me 8. 3/5 times 10 gives me 6. So we get x to the power 8 over y to the power 6. And that's my final answer there. For 23, again, I simplified some things inside the parentheses a little bit. You have a base d, so you can do 3 minus negative 4, which turns to 3 plus 4, giving you 7. And then e to the power 4 minus 1, giving you 3. All still sitting inside that parentheses with that exponent of 3 on the outside. I can then multiply that exponent of 3 to each thing, giving me this as my final answer. And the last one, let me go to the next slide so you can see how to do this one. And I'll zoom in. So my approach was the same. I started by writing my power with base g as a numerator position, subtracting my exponents. And same with base h. I have -3 minus that 3 on the bottom. And then j to the power 9, that was already sitting in the numerator, so I just took it along for the ride. And again, this is all in a set of parentheses with that rational exponent on the outside. I simplified my exponents to get +5, -6. My signs were the same, so I had to add them. And then this just came along for the ride. And then I multiplied everything with that 1/3. So I got a rational exponent for my first value here, and then everything else simplified to an integer. Last but not least, this power with the negative exponent has to move down to the bottom to its reciprocal location, giving me this as my final answer. Okay, so when you've got a quotient being raised to a negative exponent, there's a couple different ways that you can handle the problem. You can treat it, the same way that we did before. You can just multiply and get 2 to the -3 over 9 to the -3, and then of course use our properties that tells us anything with a negative exponent needs to move to its reciprocal location. So what's going to happen here is I would move this numerator to the bottom and the denominator to the top. So basically it would flip and give you this. That's option number 1. Another option, what you can do, okay, so I'll label this option 1. Another option is to flip everything inside first, then make this negative exponent a positive, and then multiply that outermost exponent. Okay, so what I can do here, I start with this, right? That negative exponent on the outside, it does the same thing. Anything that was in the numerator is going to move to the bottom. Anything that was on the bottom is going to move to the top. All of the values are going to get affected by this negative exponent. So all of the values are going to move to their reciprocal location. And then the exponent would turn positive. So I could rewrite it like this. 9/2 to the +3. And for some people, this might be a little bit easier. And then multiply the exponents to give me 9 to the power 3 over 2 to the power 3. So we end up getting the same thing no matter what. And then I can further simplify this. I'm going to have to use a calculator here real quick. Give me 1 second. So 9 to the power 3 is going to give me 729. And then 2 to the power 3, that's going to give me 8. And again, I know that this isn't going to reduce because if I looked at the 9/2 before I multiplied those exponents, 9/2 won't reduce. So this won't reduce either. So I'm actually going to use option 2, I think, for all of these. I think it might be a little quicker and easier to follow. So for 26, what I'm going to do first is I'm going to flip everything in that fraction, so b goes up top and a on the bottom, and I'm going to change that exponent to a positive. Now I'm going to multiply that 15 with those understood exponents of 1s, giving me b to the 15 over a to the 15. For 27, I'm going to flip everything in that fraction, so the 3e is now going to go up top, and the 2d is going to go on the bottom, and the 1 is now positive. And then I've got my understood exponents of 1s, but all I'm doing is I'm multiplying a bunch of 1s here. That's not going to change my exponents. All of my exponents are going to be 1s. And remember, you don't have to write an exponent of 1. It's understood to be there. So I can just drop the parentheses and write this as my final answer. Let's take a look at some more complicated examples. For 28, again, I can flip that fraction upside down. That's going to bring the r up top, the q to the bottom, exponent on the outside turns to a positive. And now this is going to be a little bit easier to work with because now I'm dealing with fewer negatives. I'm going to multiply that 9 to each of my fractions here. Let's see, 5, 6 times 9. That's going to cross reduce to give me a 2 and a 3. So I get 15 over 2. So r to the power of 15 over 2 over, and then 1/3 of 9, I can do that in my head. 1/3 of 9 is 3. For 29, I'm going to flip everything in that fraction. So everything on the bottom is now coming to the top. Everything on the top is now going to the bottom. And that outermost exponent is now positive. Additionally, I have powers that have the same base. So I can use my subtraction property where I write that base as if it's in a numerator position and subtract the exponents. I've got a matching base g and h. That's going to give me g to the negative 3 times h to the negative 2. And now I multiply. That's going to give me g to the negative 6 times h to the negative 4. And because both of them have negatives, they're both going to move to their reciprocal location down to the bottom, giving me 1 over g to the 6 times h to the 4. And number 30, and I may have to shrink 29 a teeny bit just so I've got enough space to work it all out. I can always add a page if I don't have the space, but I'm going to try. I'm going to flip everything first, so this ends up being my numerator. This all ends up being my denominator. And the outermost exponent's now positive. I have some matching bases of x and z, but I don't have any matching bases of y's. So I need to keep that y sitting in the denominator. And then when I use my property that tells me I can subtract my exponents for everything else, I'm going to bring them to the numerator. You always treat them as if they're in the numerator. So I'm going to do 4 minus negative 2, and then z to the power 0. I am going to have to move this a little bit, and maybe even shrink it a teeny bit. 0 minus negative 5. Okay, we're doing 4 minus negative 2, and then 0 minus that negative 5. And again, this is all still sitting in that parentheses with the 3 on the outside. Double negatives will make this a plus, and same thing for my base of z. So I've got x to the positive 6 times z to the positive 5 all over y to the positive 3. And this is all being raised to the power 3. So the last thing I'm going to do is multiply. Multiply that outermost exponent with all of the innermost, giving me x to the 18 times z to the 15 over y to the power 9. And there's my final answer. So again, here are some for you to try. I encourage you to pause the video, give them a go, and then I'll scroll to the next page to show you some answers. Okay, I kind of had to space everything out because these do take quite a bit of writing for me. So I just flipped everything for 31. 6 divided by 1, I can just write as a 6. So you're just squaring 6 for 31. So you should have gotten 36 as your final answer. For 32, anything, raised to the power 1, even if you looked at it as if they're multiplying here, you're just going to get a bunch of 1s. You don't have to write those exponents. They're understood to be there. For 33, you have 5b over a, all raised to the power 2. So every single value is going to get squared. And you can further simplify that 5 squared to give you a 25. For 34, I flipped everything inside first, multiplied that outermost exponent to everything inside, and then cubed that 2 to get an 8. For 35, I first flipped everything, and then we've got two matching bases. We've got a base p, so I can do 0 minus that -1. The double negatives will make that a plus, and then q to the power 7 minus 3. Simplifying those exponents gives me 1 and 4, and then multiplying the outermost with the innermost exponents gives me 7 and 28. For 36, I flipped everything in that fraction first, and then I subtracted the exponents for the matching bases. So we had a matching base e and a matching base f, but the power that has base d did not have any other matching base in the numerator, so I left that in the denominator and only moved bases e and f as if they were in the numerator to subtract their exponents. When you go to subtract for your base e, you're doing that invisible 1 minus that negative, so minus negative makes that a plus, and then you're going to get your exponents of 6 and 1 when you subtract here. All being raised to the power 5, so then multiply those exponents together, and this is what I got as my final answer. And then the last thing that I'm going to cover before I call this video done, I would imagine it's getting quite long at this point, is a couple of scientific notation examples, very similar to the scientific notation problems we've done in the past. The values that sit in front of your powers of 10s, you treat them as coefficients. We multiply and divide coefficients the way we always have. So for 37, I'm going to divide 6 and 3 to get 2. And for my powers of 10, I'm going to subtract those exponents because their bases match. This is going to give me 2 times 10 to the power 2. The last thing that you'll want to do is just verify that your final answer is in scientific notation. Remember, that coefficient has to either be a positive value that sits between 1 and 10, but not including 10, or it's got to be a negative value sitting between -1 and -10, but not including -10. This coefficient follows that rule, so that's in scientific notation. An easier way to think about it is that coefficient can only have one value to the left of its decimal point. So its understood decimal point is right here, so the only value to the left of it is that 2. For 38, I'm going to divide those coefficients of 2.4 and 0.2, and that's going to give me a 12. And then for my powers of 10, I'm going to subtract my exponents here. Subtracting my exponents gives me an exponent of +1. And the last thing I need to do is adjust my coefficient. 12 does not sit in between 1 and 10, excluding 10. So I need to take its understood decimal point, which is on the end, move it one value to the left to make that coefficient smaller. And because I made the coefficient smaller, I have to make the exponent bigger. That's going to give me a final answer of 1.2 times 10 to the power 2. Excuse me. All right, so I know this video covered a lot. I hope that the video is helpful. And as always, if you have any questions, feel free to reach out to me or any of the other math teachers if you do not have me for math. Take care, guys, and I